equations in initial valued problems. Okay. So, in order to understand what happens when we are given ordinary differential equations and we are required to solve them, so our aim in this class is basically to understand how to solve a set of ordinary differential equations whose dependent variables are suppose in y. And here I've considered a set of differential equations, and then we will see what happens when there is just one and when you have a few of them together. Okay, so suppose the set of differential equations that we have are in this format. Okay, they are in this format that dy1 by dt is a function of y1 to yn. Similarly, another differential equation is again a function of y1 to yn. And likewise, still dyn by dt is function of y1 to yn. Okay, and in order to resemble it in a vector form, we can write it as dy dash divided by dyt is a function of y, all the y's. So y with a dash. Okay. So what we are basically given in this case is the values of y at the initial time point, or whichever is your independent variable. Here the independent variable is time. It can also be x, some sort of a distance or anything. So the value of y at t equal to t naught, or whichever is your initial time point, is known to us. So all the values of y for which t is equal to t naught is y is basically y naught of all those y's, y1, y2, y3, and so on. Because we are given the values of y at t is equal to t naught, these problems are inherently called as initial valued problems. Okay, we are given the initial value of the dependent variables. Now, our aim is basically to find out y as a function of time moving forward from that t is equal to t naught. Or if you consider you're starting from t is equal to 0, then it's t is equal to 0. Or we are given the value of y as at t is equal to t naught, and we are interested in finding out all the other values of y marching ahead from this t is equal to t naught. Okay. So how do we actually proceed and solve this numerically is what we are trying to understand in today's class. Okay. So in order to keep it simple, let us consider a general case with just single variable. Just single variable. And how do we go ahead if we have a single variable and we are trying to, this is the differential equation, ordinary differential equation that is given to us, and we are trying to solve it. So we are trying to solve it and find out the solution for the differential equation. Okay. So again, what is given to us is y at some initial condition naught is equal to y naught. That is the value that we know. And to move ahead, we need to understand, have a recap of the concept that we learned in our previous classes known as discretization. So the basic idea of numerical methods is to discretize domains. Okay. So here, as we are seeing y as a function of time, what we will do is we will go ahead and discretize the time domain. And how do we do that? So we basically break it down into small equal intervals in which we are given the value of y at tn, and we are interested in finding the value of y at tn plus 1, which we do not know, and so on, tn plus 2 and so on. Okay, so yn plus 2 at tn plus 2. So the intervals in which this t is distributed, or we have broken it into small intervals, the intervals are spaced out by a value of h. Okay. So now we know the value of yn at tn, and we are interested in finding out y n plus 1, which is the value of y at tn plus 1. Okay. Now let us understand what is the I, as in at which point we want to find out the value of y, at which point of time we want to find out the value of y. So t of I is basically that ith interval, ith point, times the difference between the two time intervals. So as we have written that it is equally, the time domain is equally spaced out, and the equal space is a distance h. I mean, and a variable. I mean, what do you call it? So h is basically the constant interval in which the time domain has been distributed, right? So this ti can be written as I of h. Now moving ahead, y of I is the value of y at I, and that is basically y is equal y at t is equal to ti, and we have explained what is ti in the previous step. Now we are also given the value of the slope at the ith point, so that is y dash of I is basically y dash at t is equal to ti, and the ordinary differential equation is written in this format, that is dy by dt is basically a function of y, and it can be written as y dash, which is also a function of y. Okay. Now again a small recap that what is known to us is basically y of n at t is equal to at t of n at tn, and we are interested to find out the value of y n plus 1 at tn plus 1. Okay. So we know the value of y at tn, and we are interested to find the value of y at tn plus 1. Hence we integrate it from tn to tn plus 1 and first try to understand this expression. Okay. So in this expression we have written down integral of tn to tn plus 1 is basically, and we are trying to integrate dy by dt, and since it's integral across the time domain dt. Now we've just written in the previous step that dy by dt is nothing but y dash, which is a function of y. So we can write down the expression in this manner. Now here if we try to solve the LHS, it will simply come down to yn plus 1 minus yn. Okay, but we still do not know the expression of what will be written here when the right hand side is integrated. Okay, so we'll state our problems here. As we do not know the value of y at t between this interval tn to tn plus 1, hence we do not know its value of slope as well in this particular interval. Okay. So we will go ahead and understand how to estimate this value of slope, and firstly how to estimate the value of function at that point and then the slope. So in order to do this, we will not be doing the derivation here, but in order to find out that value of the function as well as its slope, a few techniques are used which you will probably be learning in in masters or in PhD. So a technique that is used here is an interpolation technique, as we learned in the last to last class. And Newton's backward difference formula can be used to derive an expression for the slope at tn plus 1 in that interval, basically tn to tn plus 1. Okay. So when we use Newton's backward formula and we derive the expression, we finally come down to an expression as this, which can be written as yn plus 1 is equal to yn plus h times the function yn, which is basically the derivative, plus h squared by 2 times the double derivative, and so on. So instead of doing it with the help of interpolation technique with Newton's backward method, there is an alternative method to come down to the same expression with the help of Taylor series expansion. Okay? So in Taylor series expansion, The expression for the function y of x1 will be written as y of x1 is equal to y of x naught plus h. And why this is happening here? Because if we imagine this to be the x domain, and this is x naught, and this is x1, and this is x2, and so on, they are equispaced here by an interval of h, right? So the value of x1 is basically going to be x naught plus h. The value of x2 is basically going to be x naught plus 2h, and so on. So y of x1 can be written as y of x naught plus h, and that can be expanded as y of x naught plus h times y dash of x naught plus h square by 2 factorial y double dash of x naught, and so on. Now when we take the linear terms and we omit the higher order terms, we finally come down to an expression which is known as Euler's explicit method, and the expression is written as y of I plus 1 is equal to y of I plus h times the slope at xi and yi. Okay. So why is this method known as explicit technique? Because in this case, whatever is there on the right hand side, this entire region is known to us. Okay. So even in the assignment, if you see the question that has been given to you, what basically happens is the slope is already given to us. Okay. With the help of the slope, we integrate it analytically and find out the value of the function. So basically the slope is given to us and the analytical expression of the function is also available to us. Or sometimes the function is given to us and the slope is given to us. So these both will be available, and h is the time step that we are selecting in order to compute the value of y at a different time interval or a different x domain x interval. And with the help of this expression, we are able to compute y of I plus 1. Okay. So let's take a moment here and understand what are we basically doing graphically. Okay. So let's take this curve, which is the true trajectory, this black line. Okay. Now we are given the value of the slope at xi. Okay. So basically we know this point yi at xi, and we are also aware of the slope at this point. Now what we are interested in doing is basically estimate or approximate the value of y, at xi plus 1. Okay, so we are basically interested in finding out this value. But with the help of the Euler's explicit technique, what we end up finding out is basically this value. And why is that so? Because what we are doing in Euler's technique is that we are trying to find an estimate for this point. So we write the expression as y of I plus 1. So we are basically interested in finding out this entire height, right? This entire height, this line that I have drawn here, this entire height is yi plus 1. How can we find out yi plus 1? yi plus 1 is basically going to be the addition of these two line segments, which is yi, which is already known, plus this length. Okay. Now, how do you find out that length is basically the value of yi is known. So let's not worry about that. Let's just understand how are we finding out the value of L. Now, In order to find out the value of L, if you concentrate on this triangle A, B, and C, the slope is known to us, which is, for now let's consider it as phi. Okay. Now the slope is known to us, and we know that the interval between the two x that we are trying to find out, xi we know, and we are trying to find out the value of y at xi plus 1, this interval is h. So the slope can be written as phi is equal to L by h, which is basically perpendicular by base. So your perpendicular, the distance L, is going to be phi times h. Okay. Now, since you also have the expression for L, what you just do is go ahead and write it down. So that is phi times h. So yi plus phi times h. Now you will see that what we have basically done is written the expression for yi plus 1 is equal to yi plus the slope at yi, which is yi dash, times the interval h. Okay, which is similar to the expression we had initially derived, that is yn plus 1, that is the value of y at a different interval. So if you're considering it in time domain, then tn plus 1, or x domain xn plus 1. So that is the value of y, that is yn plus 1, is basically equal to y of n plus h times the value of the slope at y. Okay. So this is the expression that we had come up to, and this was the graphical interpretation of that. Okay. So here you will notice what is actually happening. Okay. What is actually happening here, if you notice, that we more accurately, if we wish to find out the value of y at xn plus 1, it is going to be this value, right? But since we are estimating with the help of the slope at xi plus 1, the value of yi at xi plus 1, and the slope at xi plus 1, we end up finding out this value of y. So there is basically a difference in these two values, and that is the error that comes about while we are using the Euler's explicit technique. Okay. So in order to so if you take it in this way, the smaller the h value you take at this interval, if you know the value and you take a slope, so it will basically pass through the point of interest and you will get the more accurate y value. Okay. So always taking a lesser h value helps us to go more close to the actual answer, true solution. Okay. So in order to minimize this error that comes about when we use Euler's explicit technique, there are other few techniques which have been evolved, and one of the most famous techniques are the RK methods or Range-Katta methods. So let's see what happens in the RK method. So in the RK method, instead of taking only one point um, and computing the slope at that one point in order to find out the slope at the desired point, what RK methods do is it tries to compute the slope at more than 1 point. Okay. So based on at how many points the slope has been computed, the RK method gains its name in the form of RK2 or RK second order method if the slope is computed at two intervals, I mean at 2 points, or RK3 if the slope is computed at 3 points, and RK4 if the slope is computed at 4 points. Okay. So let's just get an overview of the RK method, and then we will look at the small derivation. So basically what happens in RK method is that, again, we are given the value of yn at Tn. Okay. So, and also we know the value of the slope at this point. So in RK method, what we do is we consider a point which is in between these 2 points, Tn and Tn plus 1, and we compute the slope at this point as well. So what this basically helps us is that, as you saw, the slope, if we use only one point to compute the slope at the desired point, there is a definite amount of difference or error that is coming about. We are estimating this with the help of Euler's explicit, but we are interested in finding out this point. So there is a definite amount of difference that's coming about. So what RK method tries to do is it tries to find out the slope at the given point, Tn and Yn, and also at an intermediate point, it tries to compute the slope. It takes an average of both these slopes, a weighted average of both these slopes. We will see what is meant by weighted average and why weighted average and all of this. And that is the slope, the average, the weighted average of these 2 points. It tries to estimate that slope as as a more accurate slope of the curve that we are trying to find out. That will help us to find out the value of yn plus 1 at t of n plus 1. Okay. So basically, let's go step by step and see. We know the value of yn at t of n, and also sometimes it's given, or we can find out yn dash y dash at n at which is at tn. So now what we will do is we can find out the slope at y dash of n plus 0.5. Why I've written here 0.5 is that the arbitrary point here I've selected at h by 2. Okay, so basically the n interval is added up with 0.5 in our case. Whatever your h value will be, 0.5 of that. Okay, so I'm just considering y dash of n plus 0.5. But how will we compute that value of slope at that intermediate point? In order to do that, what we do is we use the Euler's explicit technique that we learned in the previous case to find out the value of yn plus 0.5. Once we have yn plus 0.5, we take this slope of that. We take the slope at that point and find out y dash of n plus 0.5. Now that we have two different slopes, one at obviously the original point, that is y dash at n, and the slope at the intermediate point, which is at n plus 0.5, we take the average of these two, and this is claimed to be a better estimate of the average slope in between these 2 points that we are trying to find out. We are trying to find out the value of yn plus 1 at tn plus 1, and we know this value. So for our further derivation, let us take the let's take the average of these two slopes as y dash. Y bar, let's write it as y bar dash. Okay. Now, what we are basically trying to compute is something like this, where yn plus 1 is going to be yn plus h times y bar dash. So let's try and understand the small derivation with respect to how we will be able to do it. So the y and the x-axis, and this is the curve that we are trying to find out. So we are given the value of yn at t of n, and we want to find out yn plus 1 at tn plus 1. Okay. So the distance between Tn and Tn plus 1 is basically h, and we are trying to take any random point in between a Tn and Tn plus 1. This time we're not taking h by 2 because that was for the convenience, like for understanding better I had taken a point th by 2, but it can be any point in between, any intermediate point in between Tn and Tn plus 1. So let us consider a value p and q which basically lies in between 0 and 1, and hence this distance ph and qh, this distance which is going to be evaluated with the help of p and q, are going to be intermediate points in the x-axis as well as the y-axis. Okay, so we are given yn at tn and we wish to find yn plus 1 at tn plus 1, where this is the expression that we are trying to evaluate. In this expression, the only unknown thing that we have is this weighted average. And this weighted average is going to be a function of Tn, Yn, and some value h, because this intermediate point that we take depends on the distance between the 2 points, that is h. Is also a function of h. Okay. And we aim to find out this weighted average. So the weighted average of the two slopes of the slopes at 2 points, since we are finding out the weighted average of the slopes at 2 points, this is known as the second order RK method. Okay. Now, since it is a weighted average of the 2 points, we can write we can rewrite this expression as h times ak1 plus bk2, where a and b are the weights that are being multiplied, and k1 and k2 is the value of the slope at those 2 points where we are trying to compute. Okay. Now we will try and understand what is basically the expression for k1 and k2 and why is it derived in a particular manner. Okay. Now the value of k1 is always fixed, and that is the slope at tn and yn. That is the exact value that is given to us, and we use that one value as k1 in the expression. Okay, so the slope at tn and yn is basically k1. So k1 can be written as function of, k1 is basically a function of tn and yn. Okay, so let us write this expression as 1 and the second expression as a. Okay. Now we will go to the graph and understand what is happening here. How are we choosing an intermediate point? Okay, so this is the curve, the black line, and we have taken the slope at this point, and that's the blue line. Okay, the tangent. Now this entire distance is h, and we are interested in some intermediate point along the x-axis, so we write it as p times h, because p lies between 0 and 1, p times h is some value smaller than h. So this is in the x direction. Along the y direction, this entire distance is h times k1, and we are interested in some point in between h times k1. So we take that value as h times k1, but again times q, where q is also between 0 and 1. So q times hk1 is some value lesser than hk1. Okay. Now we are interested in finding the value of, so once we have figured out this, the coordinates, the x and y coordinates of this intermediate point, we are interested in finding out the slope at this point. Okay. So the slope at Tn, which was given to us, plus then we have got the intermediate point by adding this p of h. This is Tn, and if you add p of h, you will arrive at the x coordinate of this point. And this entire distance is hk1. Okay, so this entire distance is y, this much is y of n, and how much more do you go in order to get the intermediate point. So that is y of n, this distance, plus this much distance that we have come. Okay. So that can be written as so the this is the x coordinate and this is the y coordinate. Hence k2, the slope at this intermediate point, is basically a function of the x coordinate and the y coordinate. Okay. Now our aim here is basically to find out the value of k1, k2, a and b. These are the different unknowns, right? But k1 is known to us. K1 is the value that is given to us, and this, we compute the slope at that point. So that is not going to change. But in order to compute k2, there are a few degrees of freedom here because p and q are selected as random points, right? So there must be some optimal method to determine the value of p and q. Now, there is a slight derivation here, but we will not go so much into the detail. I'll take you till a point that is possible for this class, and then you will be learning about it in higher classes. Okay. So we'll go slow, and we'll see what comes. So we are basically trying to find out this slope k2. Okay. Now let's use Taylor expansion, Taylor series expansion, in order to expand this k2, where you will see that k2 will basically be f of tn and yn plus, when you are partially differentiating it with respect to the time, there are two variables here, right? There is time and there is y. So when you're partially differentiating with respect to time, the p of h is going to come outside and it's going to be the function of tn and yn. And when you're partially differentiating with respect to y, qh k1 is going to come outside, and your the function will be f of tn and yn and all other higher order terms. Now this expansion that we have written of k2 and the expansion, so this is the usual expansion of k1, okay. So these two, one I have labeled it as equation B and another I have labeled it as equation A. These A and B we are going to try and fit into this equation 1. So we will basically be replacing the values of k1 and k2. Okay. So once we replace the value, we are going to get an expression of this sort, where you will realize that the term h can be brought out common outside, and we can write this expression in terms of a and b. And when h square is taken outside common, we can write this expression in terms of the partial differential equations, where again k1 is substituted in its generic form. Okay. So there will be a little intense maths here, so we will not go into how the derivation comes up. We will more spend more time on how the graphical interpretation comes about. Okay. So this is how this particular expression comes about. So this was deriving from the RK perspective. Simultaneously, we can also use the Taylor series expansion to understand the expression, okay, where we know that the Taylor series expansion of yn plus 1 can be written in this format. And also we know that the dy by dt is basically the function of ty and n. Okay, so it can, and the value that we have of time is basically tn, so it is basically a function of tn and yn. So using this Taylor series expansion, we can write y of n as yn plus h times the function plus h squared by 2 divided by the ddt of, because here you will do a differential, okay, in Taylor series expansion, and you write down the initial function once again. Now, after this, we go into a lot of intense mathematics, so I won't be doing it here. But the idea is that we do this expansion with the help of this geometric understanding of the RK method, and the expansion that we used in Taylor series method. And finally, we compare the expansions from the geometric method and the Taylor series method and try and find out the values of A, B, P and Q, which are basically to find out the slope K2. Okay. Now there are some popular choices how they have done the derivation. Some mathematicians have done the derivation and they have reported a few popular choices of the values of A, B, P and Q, and we'll take an example of that. So one of the popular choices that is used is where they've done the derivation and they've seen that the value of A and B can be half and the value of P and Q can be 1. Okay, so you don't have to understand from where these values are coming, but there is an intense derivation which helps us to come down to these values. So you will be learning about it most probably in your postgraduate level or so. So in that case, what you can notice here is that if you replace the values of A, B, P and Q as half and 1 respectively, A and B as half and P and Q as 1, you will finally come down to this expression where it will be y of n plus 1 is equal to y of n plus h by 2. So A and B has come outside, h by 2 times k1 plus k2. Okay, where your k1 is the initial slope and k2 is basically f times tn of h, tn plus h, and y n plus hk1. So let us take a moment here in order to understand this expression. Just copy it and we'll go back to the graph here. Okay. Let's see if we can relate to how this expression can be understood in graph. So if you see here, you will understand, you will see that K1 was basically the slope at the point Tn and Yn. So it is the slope at this point, okay, which is on the curve. Now, how is the intermediate point? So based on the values of A, B, P and Q, the intermediate points are decided, right? Where the values of A and B were taken as half and P and Q were taken as 1. So when the derivation was done, the intermediate point was basically selected where? Let's first understand that. So it was selected at Tn plus h. So that is basically this entire interval. It was actually taken at Tn plus 1 itself. So it is Tn is this point plus h is this whole interval, right? So the second slope was computed at this particular point Tn plus 1. And how did they get to the y value? So for the y value, this is y of n, yn, right? Now, in order to get this extra value, h of k1, how do you get that? So this is the slope, which is k1, and this distance is h, right? So this distance that you can see here is h of k1, right? So this entire distance is going to be yn plus h of k1, okay? And so you have come up till here. So basically this is the intermediate point that has been taken. So it is not truly intermediate because it is at the end of the spectrum itself. But this is one of the points that is taken in this RK2 method where you have this slope. You compute the slope at this point and you take the average of both these points to say that that is a better estimated slope of the curve between yn and yn plus 1. Okay, so that is what basically happens in RK method of the second order. Now, since you saw that how complicated it gets to go to the graphical interpretation of RK method, we will not do the derivation. We will not do the entire derivation of the RK4 or fourth order method, but we'll try to understand what happens graphically. Okay. So, as you understood why RK second order is called second order, because the slopes were computed at two different points, right? Similarly, RK4, that is the fourth order method, is called so because the slope is computed at four different points and a weighted average of these slopes are taken in order to compute the final slope between these 2 points y and y of n and yn plus 1. Okay? So let's try and understand how exactly these four slopes are being computed. So k1, the first slope, is always the slope of the function where we know the values, that is yn and tn. Okay. Now, how do we understand how to calculate the slope for k2? So, what is proposed is that again there is a thorough derivation and the formula has evolved in that way. But let's try and understand how to get to the point in order to calculate the slope k2. So the point is basically Tn plus h by 2. So this is your Tn, this is your Tn plus 1, and this is your entire distance between Tn and Tn plus 1 is h. So the second slope is computed at a distance of Tn plus h by 2. Okay, so only this much distance is increased in the x-axis. Along the y-axis, then what happens? So if this is h by 2, so basically this distance is h by 2 and you have this red line is basically the slope k1. Okay. So if you take the slope and the base, the perpendicular distance that you will get is basically going to be, this is again your yn, plus that distance is basically the slope k1 times the base, that is h by 2. Okay. So that is how you arrive at this point and you compute the slope at this point, which is known as k2. It becomes a bit complicated to show this rectangle and find out the distance and hence the slope. So similarly, you will be able to get the slope k3 in this manner, where again you compute the x coordinate is going to be at Tn plus h by 2 itself, and the y coordinate is going to increase a little further by how much? By for k3 the y coordinate increases a little further by yn plus the same distance h by 2